Hey y'all, it's that time again. It's Math with Mrs. Peters, that crazy cat lady of Hiram High School. Today, we're going to expand our knowledge of rational equations into rational functions. All right? So, what we're going to do is we're going to show that the given function, we have two of them here, is a rational function, even though they don't look like there might be rational functions. And then we're going to verify that the new function that we've created or rewritten is a rational function. And the first thing I want to do is we're going to go over here and we are going to pay attention to this first function here. All right? Now, we are only interested right now in this part right here. That means we have a expression. All right, we're going to find the least common denominator. We're going to make equivalent fractions. We're going to do any simplification we need to do, and then we're going to determine, is what we have a rational function? Is it a rational expression? Right? So, first things first, what's the least common denominator? Well, check that out, 4n times n plus 3. Okay, and my other is 2, so my least common denominator, because 2 is a factor of 4, is 4n plus 3. Next thing that I need to do is I need to make equivalent fractions. Okay, this right here needs to be a fraction with the correct least common denominator. So that's going to be 5 over 2 times what gives me 4n plus 3. Real quick, let's see. I need another 2n plus 3. And when I do my magic math, I get, what do I get? I get 10n squared plus, what is it? 30n? Yeah, that looks right. So I'm going to replace the circled fraction with my new one. So what I actually have now is going to be 3n over plus my new numerators, 10n squared plus 30n, okay, over my least common denominator. And you know what? I'm going to write this least common denominator in factored form. That's what I'm going to do. Okay, so all this over here is going to go away because now I have my new function here. Whoops, it got silly there for a second. There we go. So here's my new function. Am I done? Oops, I forgot a 30n that there. There's an n on the end of that. Isn't there? Isn't there? Yeah, there is. Okay, so now I need to combine like terms. So that means when I combine like terms, I get 10n squared plus 33n over 4n plus 3. So far, so good? Now, my question is this a polynomial? Okay? Well, yeah, that's a polynomial. And if I just wanted to go back to my original denominator, because I really don't need to simplify here just to determine whether or not I have a polynomial, is this a polynomial? Well, the top one, I do not have a fraction exponent. I do not have a fraction in my top anywhere, so I don't have to worry about a variable in the denominator. I have fractional exponents, and so what was the fourth one again? No fraction exponents, no negative exponents, no variables in the denominator, and no variables under the radical. I don't see any radicals. And guess what? Both of these are yes. They are polynomials, which means that my function is a rational function. So, with that said, I'm going to leave you with this one right here to do. Okay, again, make equivalent fractions, combine like terms, and then determine, do you have a rational function? I'm going to leave you that one to do. Okay, now, write a rational function, h of x, using the given functions f of x and g of x. Verify that both possible functions are rational functions. First thing I'm going to do is I'm going to verify that this is a polynomial. Yes, that's a polynomial. Okay, the bottom one, yep, it's a polynomial too. So, when I decide to come along and I write p of x, some function that has 2a plus 1 on top and a to the third minus 2a on bottom, and since both of those are polynomials, this is a rational function. And the reasoning is because both my numerator and my denominator are polynomials by the definition of polynomials. Now, I also want to know if q of x, which would be a to the third minus 2a over 2a plus 1, is that a rational function? Well, by definition, since the numerator is a polynomial and the denominator is a polynomial, I can say yes again. Again, my reasoning is that my numerator is a polynomial. It met the qualifications for polynomial, and that my denominator is a polynomial because it met the definition of a polynomial. And by both of those numerators and denominators being polynomials means I have a rational function. I have a rational function. And I'm going to ask you to do the other one. Yes, you can do this. I know you can. I'm very proud of you. If you have any questions and you're not sure that what you wrote down is correct, come to tutoring or come to class and ask me. I'll be happy to help you out. Y'all take care. I know you can do this. Talk to y'all later. Bye.